Hello everybody, welcome back to calculus class. Now Mr. Newcomer is of course away today. He is very busy sitting around downtown at the courthouse waiting to be on the jury. So here is some notes and some help to help you finish up with functions. Now throughout here there's some things I'm going to skim over. So anything I skim over from the notes, I would like for you to go to the textbook and complete the missing pieces. I'm hoping that some of the explanations that we will go through in this video will help you to better understand the idea of functions and their purpose. Please make sure that you come to me with questions once I do get back. With this video, feel free to pause it, feel free to skip ahead, whatever you like, but hopefully all of the information that is here in this video is going to help you to be able to come close to finishing the homework assignment. The first thing that I wanted to mention, and there was a lot of confusion, I think, between the difference between the two different forms of functions. The thing is, just like equations, functions can really be thought of in two different ways. Functions can be equations. Okay, so here we have an example of an equation. It really doesn't look anything different from what we've seen in algebra, but it is a function. But at the same time, functions can also be viewed in graph form. And sometimes it's going to help for us to think of them in the two different forms. So if something confuses you about a function, maybe you need to be looking at it in a different form. Maybe you're looking at the equation and you need to look at a graph of it, or vice versa. Domain and range is also another issue that it becomes a lot simpler to understand if you're talking about it in the two different forms. Take an equation, for example. Domain is pretty simple. Domain is all of the possible numbers that you could possibly put in for x. Now, to figure out the domain of something, it's actually more simpler, since there is thousands upon thousands of numbers, to figure out what x cannot be. Looking at this fraction, I know that x cannot be equal to 6. Otherwise, there would be a 0 in the denominator. That is called implicitly defining the domain, when it's something specifically from the equation. But in real life, a lot of times we have limitations. We have boundaries or things that are set by the government or by policy, or like this explicitly defined domain. Implicitly means that there's just something, a part of the equation, that you cannot allow. Explicitly is basically an extra rule that is set upon it, usually in the form of a conjunction. Let me remind you that you can write your domain in terms of a conjunction like so, but using set notation, not to be confused with an ordered pair, would be an identical way of noting the interval. But range is a little more complicated to comprehend. Range is going to be all of the possible numbers that you could end up with as f of x if you plugged in every single value of x that was even possible. Now, finding that algebraically would be pretty difficult depending on what the equation is, because you could have thousands upon thousands of possibilities. So sometimes looking at the graph might make it a little easier. The domain is all of the different values that you could get on the x-axis for a function. So if you're looking at a picture, you can define the domain as starting at a minimum point, going to a maximum point, similar to our domain defined by the equation. Now, the range is going to be practically the opposite. Look at all of the different values that you could have for your y-axis. Now keep in mind that eventually we're going to stop calling it the y-axis. Really, it's the f of x axis. This interval from the lowest point to the largest point is going to be the range. Domain goes along the x-axis, and range is all the possible numbers that would go along the f of x or y-axis. I just wanted to point out that with domain and range, it's not always going to be an interval per se. Take this example. This is an example of some sort of rational expression. You could try to figure out an equation that would mimic this. But my point in showing you, because these lines go on forever into infinity, really, our domain includes every single real number possible. Same as our range. For this equation, the range is every single number possible because the lines are going off into infinity. That is absolutely a possibility when considering domain and range. There might not actually be any limitations for certain functions. We're going to move away from talking about one-to-one and onto too much. I've decided, at least for now, it's definitely not going to be on the first test. But as we go through the year, if it comes up again, maybe we will reevaluate that. But at least for this first quiz/test, we're not going to worry about one-to-one or onto anymore. Look over the examples in the homework and really try to get a grasp over what it means, because it is really an important concept. If you get it now, it's going to really, really save you a lot of grief in your college math classes. The graphs of functions especially become super, super useful, especially because that's the easiest way to tell if something actually is a function or not. Well, keep in mind that really a graph of a function is going to be all of the ordered pairs where you have the x-axis, the x point, all of the members of the domain as the x-coordinates, and of course its image as the y-coordinate. So every single number in the domain as well as its image makes the graph. The vertical line test is a really nice way of telling whether something's a function or not for sure, because it basically says that if you have a vertical line, no matter where it is on the graph, it cannot hit 2 points or else it's not a function. Take this first example. You could draw lines wherever, but that vertical line is only touching all of those places in just one place. An ellipse, like the second, because a vertical line is touching at 2 different places, that ellipse is automatically not a function. If any vertical line can hit a graph in more than one place, then that graph and its equation that goes along with it is automatically not a function. Now, one of the most important things about calculus is going to be really using these graphs that we're used to, especially the ones that are quite a bit odder, the ones that aren't straight. In your textbook, you have pictures of what all of these different functions look like. Pause the video now and go to your textbook and actually sketch a rough drawing of all of these different functions. Remember, we know what some of these look like. Squaring a function is actually what we know as a parabola. If you have any questions, consult with the book and see me either tomorrow or the next day before you get to class. The trig functions are also in the book, so make sure that you include their images in your notes. But I believe that next class on Thursday, we are going to spend a lot of time on trig. because unless every single one in the class can tell me off the top of their head what sine of 5 pi over 6 is, then you definitely have a lot of trig that you need to practice before we have our first quiz. So start refreshing your trig over the next couple of days as well. Next weekend is going to be a big weekend for trig practice before we have some assessments next week. Now, what's so nice about memorizing what the shape of a particular type of equation is that transforming it in different ways becomes very, very simple, because you can just start adding or subtracting elements to that equation. For example, if you want to move something to the right, we're talking about the graph of something, whether it's absolute value or sine or a linear equation or a parabola, whatever. To move it to the right, you need to subtract whatever number of units you want from that x. Again, to move it to the left, you add. If you want to move it down, you subtract that number, and to move it up, you shift it up. But what's the difference? What is the difference between doing that and shifting to the right? Basically, how it works, say we have this very simple example of a parabola. That is the standard. It's just a standard parabola. If you wanted to shift it to the right 2 places, you would have to change that x to a parenthesis with x plus 2. Doing that is going to shift to the right 2 spaces. Okay. Oh, I'm sorry, to the left. So if you add 2 inside these parentheses with that x, then you're going to shift to the left. If you wanted to shift it to the right, you would have subtracted 2. Now, on the contrary, if you just wanted to shift it down, well, you don't really have to change the x squared. You're just going to add an additional term afterwards. Now, reflections also become important. You can turn a parabola upside down just by putting a negative sign in front of it. If you want to flip it on the y-axis, like make it a mirror image, you can. Again, put that negative x, but inside a set of parentheses where that x was. Reflections around the origin, you would just do both. Reflect it around the x-axis and reflect it around the y-axis. It's a pretty simple concept to understand. I would recommend just start playing with your graphing calculator. Pick a standard function like y equals x squared, or maybe do it with a cubic function or an absolute value function. Just really play with it and start changing all kinds of things and observe how it is changing. There's 3 main types of functions that we're going to be working with. For most of the year, we're going to be focusing on polynomial functions. You've seen polynomials all throughout algebra, but there's going to be a lot of times that we're going to talk about trigonometric functions as well. Really, you shouldn't be that scared of trig, although I think probably a lot of you are. It's really important that, unfortunately, the best way to make trig an easy subject is to bite the bullet and do a lot of memorization early on. But don't worry, don't panic. I have a lot of little tricks and secrets for how you can make memorizing trig issues very, very simple. So, although I want you to be clear that you are going to be doing a lot with trig in calculus, I don't want you to panic too much because I am going to help you through it. Exponential and logarithmic functions are equally as common. Often you won't see them until you get to Calc 2, but there are going to be times where we're going to start looking at exponential and logarithmics. For the rest of the notes up into the next page, you can pause this video and go to the textbook to actually try to fill in the rest of these notes from pages 24 and 26. Okay? Nothing that's going to be super, super, super important for the test, but obviously things that are important for you to understand. Now with functions, one of an idea about functions that is it's pretty difficult to comprehend for a lot of people is the idea that you can combine two functions. Now, you can combine them by adding them together, you could combine them by subtracting them or multiplying them. That's pretty simple. But combining them by composition is a little more complicated. Say you have f, a function, and a second function, g. You can combine them with a composite function with this notation. Now, don't confuse that dot with a multiplication sign, because that open, hollow, white dot does not mean multiplication. What it really means is that you're going to take g of x, that second function, and you're going to stick it in the function f. Now, so look at example 3, what we have down there. You want to find f of g of x. That's how you would read that. F of g of x. What you're going to do is you're going to take g of x and you write it down. 2x squared minus 1. Putting it in parentheses always helps me. And what you're going to do is surround that function, g of x, with everything from f of x. Basically taking that g of x and substituting it in for the x of f. So I put 3 in front of it, and I put plus 4 afterwards. Now, usually you would then simplify a little, distribute, for example, 6x squared minus 3. Then you have some like terms that you can combine. 6x squared plus 1. Here you have the composite function f of g of x. Taking g of x and substituting it in for the x in f. You can also do it in reverse. G of f of x would be taking f of x and substituting it in for the x in g. Just don't forget, you usually will have to FOIL, collect like terms, do a little bit to get it into some standard form. Composite functions is going to be something that was going to take a lot of getting used to for some. Look at some of the examples that are in the textbook. Really try to look over them and really work hard at trying to grasp your mind around those problems in the homework. Because come chapter 2, composite functions and your understanding of them is going to make the lot of difficult topics much, much easier if you understand them in advance. The last thing that I want to mention is in the last couple of class periods we talked about x-intercepts, okay? One important thing to note is that eventually we'll stop calling them x-intercepts also. There's a lot of new vocabulary in calculus. What we like to call x-intercepts is that if you have a function f, any x-intercepts of f, we call them zeros of f, which really are just solutions to the equation f of x equals 0. So whenever you hear us saying future down the line in the next couple months, if we say find the zeros of f, just realize that that's something we've already done before. Zeros of f equal the x-intercepts of f. The very, very last thing that we need to mention before I stop rambling on here is there's another term, whether a function is considered to be an even function or if it is considered to be an odd function. And this is pretty dang close to how we defined symmetry. So we've done this pretty carefully already. If you plug in negative x in place of the variable x and you end up getting the same function, well, then you say that you have an even function. But if you plug in negative x for a value of something and what you end up getting is the opposite or the negative of the original function, then you call it odd. Again, look at the examples in the textbook for a little more information on this, but it is very, very, very similar to our tests on symmetry. I know this was a heck of a lot in this video. I hope that you were able to skip around if there was something that was easier for you. Whenever we have a video like this, you don't have to listen to the entire thing. But this is a resource for you, especially when I'm not around. For next class, you should be able to come pretty dang close to doing most of the problems in the assignment. Problem set 3. If you still need help with anything from problem set 3, you need to be emailing me. If I do not hear from you, then I am expecting that you figured it out and yet you're doing okay. So if you're struggling, you need to come up with questions and you need to contact me. I am hoping that I will be back in school on Wednesday, so you can come in to see me for help. So just check in on Wednesday, and on Thursday we are going to do one last review over problem set 3 before we do a big encompassing trig review. So it'll be really exciting, and we will for sure have some sort of assessment on Monday. And depending on how everybody's doing, that'll determine what exactly is on it. But as of right now, anything from problem set 1, 2, and 3 is fair game. Okay. Good luck. Email me with questions. Sayonara.